Okay, good evening, ladies and gentlemen. This is Professor David J. Delos It's February 16, 2025, and the time is 20:54. That's a military time. That will be 8:54 p.m. My topic for tonight will be a long video format topic, and this is a continuation of my long video format topic, DC circuit. Okay, before I will continue the discussion for tonight, I just would like to correct an error, an erratum, something like that, with regards to lesson number 25 and 26. I changed the title of the subject matter because I have intentionally reverse it. The title of the topic for lesson number 25, it should be the delta to y transformation equation. Actually, lesson number 25 is it should be delta to y, not y to delta. And lesson number 26, it should be y to delta. For 25 and 26, I just have discussed the importance of the concepts. And for tonight, it should be lesson number 27. This is a continuation of 25 and 26. Because lesson number 27, this is where I found the error on the title. Because for tonight, I will be presenting the so-called derivation of the formula for a delta to y transformation. That's why I have known that I interchange the title for 25 and 26. So for tonight, I will be deriving the formula on how to change a delta configuration to a y configuration. Sometimes by just memorizing formulas, you could interchange it. But if you have passed by the so-called derivation, you will see the so-called error. There is an error on the interchanging. Okay, let's proceed. Lesson number, or the lesson for tonight will be lesson number 27. And this is still a continuation of my DC circuit. I am almost done with the study of DC circuit. So, lesson number 27, I just would like to present the derivation of the formula for a delta to y transformation. Okay? Not y to delta, it should be delta to y. I will just give you the derived formulas before I will bring out the derivation. These are the derived formulas for delta to y transformation. Meaning to say, if we are given the delta connected loads, to compute for the equivalent y loads, this will be the formula. So in here, the resistances R1, R2, and R3 should be given. That's the given delta load. And supposed to be, we will compute for the equivalent of this in terms of y. So regarding the equations, okay, R1 now, okay, will be these equations here. Actually, the denominators are the same. R1. Hold on. R1 are given, excuse me. I haven't changed the formulas. This should be RA, this should be RB, and this should be RC. So for A should be R1, and this will be R2. RA will be R2, yeah. We are following the derived equation. This is still R1. This will be R3. So for RB, okay, it should be the product of R1, R3. This should be R3. Okay, and for R sub C, it should be R sub 2 and R sub 3 all over the same denominator. So I will go back to this. It will be R1, R2, R3. This will be R1. Anyway, it's still the same. R2, and this will be R3. This will be R1. This will be R2, and this will be R3. Oh, this is the correct formulas now. RA, RB, and RC. The given loads are actually R1, R2, and R3. So we will be computing for RA, RB, and RC, and these are the formulas. So the right hand side are all the values on the given delta load. That's why the title of the topic will be from delta to y. Okay? This should be the correct formulas for a delta to y, but the emphasis for tonight will be the derivation. How come it come out like this? Okay, let's try to bring out the derivation. To derive the equivalent of R1, R2, and R3 in terms of the y connected equivalent, this will be the derivation. This will be point X, point Y, and point Z, and this should be the neutral. And again, if we try to take the delta equivalent, this is still point X, Y, and this is Z. Consider X and Y, meaning consider this X and Y here. We'll try to put our what you call this multi-tester over here connected to X and Y. Okay, so we'll be connecting our tester here, and we will compute for the resistance. Okay. Okay, and so with the other one, we'll be connecting it here. Okay, we'll get our multi-tester, we'll tap it here. Okay, we'll get the tester still, we will tap it here. Still the same X and Y. So considering terminals X and Y, okay, we will take the resistance. If we are on the Y equivalent, if we try to put our tester here, okay, R sub C will not be included because it is an open circuit. So what will come out will just be simply, it seems R sub C is missing. If we try to tap the multi-tester here, so if we try to take the multi-tester here and we get the resistance, the reading will be the value RA plus RB. So this is RA this is RA plus RB. Okay? And if we try to take the equivalent of this in terms of delta, we will be moving on the delta side. So if we try to tap our multi-tester here, okay, this is included because this is a closed circuit, right? So it seems R2 and R3 is in series, okay, and this series equivalent is connected in parallel with R1. So just in case we get the reading here, we know how to compute for the resistance of two branches which are in parallel. It should be the product of the resistances all over the summation of the two individual resistances. But the second resistances are actually the sum of R sub 3 and R sub 2. So if we try to take the single equivalent of this one, it will be the product all over the sum. Okay, that's the concept on how to get the single equivalent of two resistances in parallel. This one is to be considered as one only. because we take the sum. So it should be the first one times the second one all over the summation. The sum of R1 plus the second one, but unluckily the second one is the sum of R2 plus R3. So if we are considering the delta, if we try to take the resistance here, the single equivalent of this one will be the product all over the sum. We call that equation number 1. Right? Consider terminal XA. XA here, this one. If we try to get our multi-tester here, okay, we will take the reading R. The tester will be here, terminal X and Z. No, yeah, Z. This will be an open circuit, so RB will not be included. So if we try to take the total resistance here, this RA and RC is in series. So the right hand side is RA plus RC if we are on the Y side. And if we try to take the equivalent of this on the delta side, X and Z, okay, we'll put our multi-tester here, and we'll try to read the reading, the resistance. So if we try to put the tester here, R1 and R3 are in series, and the single equivalent will be connected in R2. So if we try to take the single equivalent, okay, it will be still the product all over the sum. So it will be R2 times the second resistance, and the second resistance is actually the sum of R1 and R3. This is R1 and R3 all over the summation, and that will be equation number 2. It's easy to understand the formulation of this one if you go back to the circuit. So we are done with the terminal X and Y. X and Z will go with the terminal YZ. We'll get our tester here. We tap it here. Okay. We'll do first Y. Okay. We'll take the resistance. We are on the terminal Y and Z. So if we try to tap our multi-tester here, RA will be an open circuit, so it will not be included in the computation. So the total resistance of the reading should be the sum of RB plus RC. So this is RB plus RC. On the delta side, if we try to take the equivalent, we put the tester here. Okay. R1 and R2 will be in series, and the single equivalent of R1 and R2 will be in parallel with R3. And if we try to take the single equivalent as a reading for the resistance, again, same formula, product all over the sum. So it will be R3 times the single equivalent of R1 and R2. This is R1, R2. First one, second one, unluckily the second one comprises of two resistances which are in series, R1 and R2, all over the summation. That will be equation number 3. So actually, to compute for the value of RA, RB, and RC, if we are given R1, R2, and R3, I will try to check my camera. Still fine. We are now given 3 linear equations involving 3 unknowns. So by using our knowledge of the study of algebra, we could compute for RA, RB, and RC. And to do that, it is something like this. If we try to subtract equation number 2 from number 1, if we try to subtract, okay? If we try to subtract it, RA minus RA, this will actually cancel out. So I place it here, RA, okay, minus RA. And this RB here is still RB. Okay. We will subtract RC because we subtract 2 from this, right? And for the right hand side, I just expanded this one so we could visualize when we try to cancel something. So R1, R2 is actually R1, R2. R1, R3 is R1, R3 all over the summation. And if we try to subtract 2 from 1, the overall sign here will be negative. Right? So I will now insert the sign. this is plus, this is preceded by negative sign. So this will become, the product of this one, R1, R2 will now be negative. And the product of R2, R3 is still preceded by negative sign because the operation is subtraction. Still minus R2, R3 all over the same denominator. Okay? And add equation number 3. I just expedited the writing because we lack a space. After subtracting 2 from 1, we will add equation number 3 to the sum. So the left hand side will be RA plus RC, or RB plus RC. That's the right hand side if we add 3 on the sum. And for the right hand side, it will be the product of this one, R1, R3, R2, R3, all over same denominator, R1 plus R2 plus R3. Okay? The sign here didn't change because we add 3 to the sum of 1 and 2, the subtraction of 1 of 2 from 1. So this is still plus. This is still plus and plus, so we could try to make some cancellations now. This RA here cancel with this, okay? And this RC here cancel with this. That's the left hand side. If we try to subtract 2 from 1, then we will add equation number 3 to the sum. Okay? And for the right hand side, since the denominator are all the same, that's an easy one. So we'll just combine the numerator now. The numerator, this is R1, R2. This is negative R1, R2. So actually they cancel out. Okay? R2, R3. Where's R2, R3? This is negative R2, R3, right? This is plus R2, R3. So actually they also cancel out. So the resulting numerator now on the right hand side after the cancellation, this is R1, R3, right? This is R1, R3. So that's twice R1, R3. This is R3. Right? And for the denominator, it will be the common denominator. That is R1 plus R2 plus R3. The left hand side, it will now be something like this. This is an R sub B. This is an R sub B. They didn't cancel out. So twice R sub B. Because RA cancels, R sub C cancels, but R sub B, there is one here, there is one here. So this is now twice R sub B. And this should be equal to twice R1, R3. I just copy this one. All over the summation R1 plus R2 plus R3. And actually, we can cancel this to here. To compute for RB without this to here. So as a final formula on the computation of the value of R sub B, it will be the product R1, R3 all over the summation R1 plus R2 plus R3. Okay? That's for a delta to Y transformation. Meaning to say, if we are given R1, R2, and R3 to compute for R sub B, it will be the product R1, R3 all over the summation. That's it. So, okay? If we try to derive the other formulas, we do not need to go back again to the computation. We'll just follow the, what you call this, how this RB was set up. So if we try to compute for R sub A, because actually we could present now the summary on how to compute for the Y equivalent. It will be the product of the two adjacent Y's all over the summation. So if we try to compute for R sub A, this is R sub A. Okay? By following that one, it will be the product of the two adjacent resistances connected in delta, R1, R2. So this is R1, R2. If we try to compute for RA, all over the same denominator. And for R sub C, if we try to compute for R sub C, the resistances adjacent to it on the delta connection is actually R2, R3. So the numerator in the computation for R sub C will be R sub 2, R sub 3. So this is R sub 2, R sub 3 all over the summation of the resistances which are given in delta. It is all this. That's the so-called derivation of the delta to Y transformation. That's where I noticed that my lecture on lesson number 25 was interchanged, because without going back to the so-called derivation, I don't know that I interchanged the formula, right? So I'm telling you, lesson number 25, the title should be, I edited it already on my YouTube channel. It should be the transformation from delta to y. And then for lesson number 26, it will be the opposite. It will be the transformation from y to delta. Because the next time around, maybe I will present the derivation of the formula on the transformation from y to delta. Because for tonight, what I presented is actually the derivation of the formula from the transformation delta to y. Meaning, if we are given the delta loads, we could compute for the equivalent y loads of this by using these formulas. And these formulas came out from the so-called derivation by presenting this one. So like what I said, RA will be R1, R2. RA will be the product of these all over the summation. RB, okay, RB, it will be R1, R3 all over the summation. And R sub C will be the product R2, R3 all over the summation. It is C. RA, just be sure that the numerator should be the correct one. It should be the resistances adjacent to the resistance to be computed in terms of y. R1, R2. For R sub B, it should be R1, R3. And for R sub C, it should be R sub 2, R sub 3. It's the product of the two adjacent resistors, which are given in delta, all over the summation of the resistances and delta. That's the derivation of the formulas or the transformation formulas from delta to y. Okay, that's it, guys. It's very nice to hear or observe if we could observe the so-called derivation of the formulas. Because by just memorizing the formulas, we might interchange something, right? So for this one, I just discovered that I interchanged the formulas from delta to y, y to delta. That's why I edited my lecture on lesson number 25 and 26. The title for lesson number 25 should be the transformation from delta to y. And for lesson number 26, it should be the transformation from y to delta. Okay, for delta to y, it should be the product of the adjacent over the summation. Product of the adjacent over summation. Product of the adjacent over summation. For the reverse of this, it's a different formula. That's why the next time around, I might bring out the derivation of the formulas, the transformation from y to delta. So for those of you who would like to watch my channel is at youtube.com/@ProfDavidJDelosReyes. If you want to share it, please click share. For those of you who do not know yet that my channel comprises of long video format topics on differential calculus, it's complete syllabus, integral, complete syllabus, differential equations, complete syllabus, advanced math, complete syllabus, AC circuit, DC circuit, algebra, and trigonometry. So for those of you who would like to take up engineering, this is good for you guys. Because if you watch my channel on my long video format, okay, the subject matter, it's almost there. But the one I followed was the syllabus for the subject matters. For my short videos, it comprises of electronics and some other things. So it's a make-up of things on my short videos. There could be electronic things, some survival things, or anything that is favorable to mankind. I mean, if it will bring goodness to mankind, I presented it there. Good evening from Los Angeles. This is Professor David J.